So, here we will be talking about atomic force microscope. Microscopy has always been the trend by virtue of which we are able to reach to the microscopic level and to the nano level. And the technologies keep on changing, modifying, and every time we come up with better technology uh, to monetize, to observe the materials, to observe their surfaces, to see the action of various uh, atoms and molecules that are involved in some kind of structures. So microscopy, it's not the only tool that's being used in case of some particular field of science. Its importance is ranging all from organic matter to inorganic matter. The range of examinations are out there, and people are coming up with better technology so that we can observe the morphologies, the surfaces, and can analyze the very basic nature of atoms and molecules at very small scales. So here in this video, I'll be talking about the atomic force microscope. And this atomic force microscope, it's a powerful imaging instrument that allows us to study the surface morphology, topography, and the mechanical properties of a wide range of materials at bulk scale as well as at the nanoscale. So it operates by scanning a tip, a sharp tip across across the surface of a sample and measuring the force between the tip and the sample. Now, the very first important point about this microscope is that it consists of a small cantilever. You can see here is a cantilever with a sharp tip attached to its free end. The cantilever is made of flexible material such as silicon or silicon nitride kind of materials are used in manufacturing this cantilever. And then the sharp tip is brought very close to the surface of the sample, typically within a few nanometers. As the tip approaches the surface, various forces come in action, like van der Waals force come in action, the chemical bonding force come in action, and electrostatic force come in action. So the various kinds of forces come in action when when the tip of this cantilever is brought very close to the surface of the material. Now, the forces acting between the tip and the sample cause the cantilever to deflect. Certainly, it will cause it to deflect. The deflection of the cantilever is typically measured using a laser beam. It's used by a laser. A laser beam is being used here to check the position of the cantilever. And the back of cantilever onto a position is a photodiode. It's a very sensitive photodiode. So now the action is going on. The deflection signal is used in the feedback system to maintain a constant deflection or the force between the tip and the force between the tip and the sample. The feedback system adjusts the position of the tip by moving the scanner in 3 dimensions. That's fine about it. Keeping the deflection constant. The feedback mechanism allows for the precise control of the tip sample interaction, enabling the imaging and measurement at the nanoscale. The tip raster, the tip it's basically rastered, it's raster scanned across the sample surface using piezoelectric scanners. As the tip scans, the deflection of the cantilever is continuously monitored and recorded. The recorded data is used to construct a topographic map of the unique surface, representing its height variations with nanometer resolution. Uh, this AMF it offers various imaging modes such as contact mode, tapping mode, non-contact mode, and dynamic mode, each with its own advantage and application. In addition to the topographic imaging, this atomic force microscopy can be used to measure uh, other properties, including surface roughness, friction, adhesion, and elasticity. The resulting images that are there, they are being displayed on the monitor or recorded digitally for the further investigations. Uh, these AFM systems provide tools for quantitative measurements, surface manipulations, force spectroscopy, and other advanced image techniques. It's worth important to note here that this atomic force microscope under ambient conditions, meaning samples can be imaged in air or liquid environment. Additionally, AFM can be used to study a wide range of materials, including semiconductors, polymers, biological samples, uh, and so on. So the advantage in case of atomic force microscope here is that we don't need any kind of vacuum. We can perform the experiment where we can have intermediate presence of air, because there's no involvement of probing of the particles from the tip of the cantilever to the surface of the sample. So there happen to have some advantages of atomic force microscope over other microscopes that we have already discussed, like scanning electron microscope and scanning tunneling microscope. In both of these microscopes, we saw that there's a need of generating a vacuum inside the chambers where this all photography has to be executed. But here, in case of atomic force microscopy, we see that we can perform the experiment even in the situations where there is the presence of some moderate quantities of air or in liquid.